All right, good morning, everyone. My talk is about high-fidelity simulations of supersonic plume-induced cratering on a granular soil using a hyperbolic model. And you will see immediately that these simulations are directly applicable to the PSI problem in hand because of the configuration. Additionally, they are predictive simulations in the sense that once we know the initial conditions and once we know the properties of the soil, etc., we can predict what is going to happen. Next slide, please. So why do we need a hyperbolic model? First of all, you see the configuration is that of the jet impinging on a not necessarily flat surface, and excuse me, the volume fraction is here, for example, for the undisturbed soil, 0.45. And then next to it, to the right, you see the vision that we all have of the crater. The crater has a compaction zone, and with a depth, a lower depth and an upper depth, that is a crater floor, and a diameter of the crater. Now, the particles are incompressible. And it is well known that for an incompressible medium, the model of the Navier-Stokes equations for multi-phase flows is not hyperbolic. So we've shown that in the previous publication. So what happens if it's not hyperbolic? In our case, for example, it was hyperbolic in 98% of the domain. But in the 2% remaining of the domain, there were very important regions in which it was not hyperbolic. So at the bottom of the crater, at the crater surface, where there is a flow particle interaction, and in the ejecta. So it's clear that we need a hyperbolic model, and I'll show you why. In the middle part, you see that these figures obtained with a hyperbolic model that I'll describe in a little moment. So this is a pressure. We're looking first at the pressure in a cross section, and we're looking also at the top view at 3 different times. T star equals 68, 128, and 187. At 68, you can see that the plume has just impinged on the soil. You can see that there is that formation of the shock at z equals 0, which is the surface. And if you look at the top part of the view, which is adjacent to it, you can see already some pressure waves that are starting to expand. And at 128, you can see a progression. You can see clearly now the pressure wave, same thing at 187. Well, what happens is that as a jet impinges on the soil, the pressure makes an imprint on that soil, and pressure waves start propagating. And we know very well that you can't propagate waves without having a hyperbolic model, which of course justifies a hyperbolic model. Next slide, please. So how do we introduce a hyperbolic model? You can see that picture of the particle that goes with a velocity us, the solid, and around it is something that's called the added mass. The added mass is gas that is basically in a boundary layer and in a wake of the particles that travels with the same velocity as the particle. So the fluid travels with its own velocity, and the added mass travels with the velocity of the particle. So it's very important to define volume fractions that are indeed representative of the fact that added mass travels with the velocity of the particle. And you can see the source term of the added mass just above that figure that has to do with the difference between the normal velocities at the boundary of the added mass and the normal velocity of the fluid. And we have a model for it that is actually a model that is taken from the literature. I like also to point out that in the model that if the C star M and the Cm are equal, then this added mass source term is 0. There is an equilibrium. Next. Next. Okay, so the governing equations, no. Previous. Okay, the governing equations are Eulerian for the fluid, Eulerian for the particle medium. For the gas, we have large eddy stimulation equations for compressible flow, where the large scales are computed, small scales are modeled. Solids, the equations are akin to kinetic theory, and we have transport properties, and several terms are modeled semi-empirically with well-known models. So the governing equations are conservation equations, equations of state, transport properties, interface interaction models. Next. Next. Okay, so how does added mass behave during the crater evolution? Here's an equation that one can derive for the added mass that has a convective term, a source term, and a velocity difference term. So let's look what is added mass volume important. So here we look at two different times, and we can see that the added mass is more important in volume than the volume of the fluid that does not travel with the particle velocity, at least in the part of the crater that is compacted, in the red part, because you see that there is two, okay? And as a matter of fact, if you see the ratio of the added mass to the volume of the fluid, you can see that is 66% of that. And it is also a very important part. The volume of the added mass compares to the volume of the soil itself, the particles itself, at 63% at the interface between the fluid and the particles, and also in the ejecta. Let's go to the next slide. So the convective term is seen to be very important in the transmitted shock and in this cup that is formed at the surface of the crater. The source term and the velocity difference are very important at that particular interface at the walls that are formed in a crater. So there is a totally different region, locality, where the convective term and the source terms and the velocity terms are important. Next. Okay, so here are some crater shapes, isosurfaces for three different conditions. Here, on the left-hand side, the ratio of the fluid density to the ambient density is 2, then in the middle 7.5, and then 12. You can see isosurfaces looked at in cross, at least perpendicular, and also top views. On the left-hand side, you can see this very small and rather round crater that is formed. It's a conical crater that is very deep and has been shown yesterday as different from the more parabolic and double craters that you will see on the right-hand side. And it has nothing to do with the cohesion of the soil. It has to do with the ratio of the density of the fluid by the density of the ambient. And you can also see that for the crater in the right-hand side, there's these ridges that are all over the inside of the crater. These ridges are not running on horizontal terrain. Each ridge runs over terrain at several altitudes. So in other words, the crater has a very complex shape inside. Next, please. Okay, so what's the crater evolution? We're looking here at the case where the ratio of the densities is 12. And we're looking at three different times. The top figures are for the density gradient magnitude and 3 grams per meter to the fourth. I'm almost finished. The bottom is for the volume fraction of the solids. You can see that as a jet impinges on the soil, it has a stagnation region from which there is a reverse flow that shears the surface of the soil and forms what you see at the bottom, that double crater. So the inside crater is formed by the jet, the outside crater is formed by the shearing of this reverse flow of the soil. And you can see the progression right here. Now let's go to the next. Next. Okay, here is what is the importance of this added mass. You can see that at both times that I'm showing, the added mass in the soil is like 25% in volume of the entire volume of the soil containing the particles and added mass. And you can also
go to your summary slide, please.
The summary is next, okay?
Great.
And on the right-hand side, what I have are some, okay? Added mass is needed for the mathematical and physical consistencies, does not change the global physics, instead it has a local impact. And after an initial transient, there is an equilibrium that establishes between the added mass volume fraction and the solid volume fractions, which may lead to model simplifications. Now, the influence of the time scales has been addressed in a paper that has just been near acceptance for publications. And we also indicated some experimental data at intermediate crater heights where you can actually validate this model. Thank you very much for your attention.